So for those of you that did join us for the first webinar, you will recall that we focused a lot on some of the free tools that can be available to you to introduce the idea of using computer software to help alleviate some of the pains that are associated with method development. As we know, this can be a tedious process and it can actually be quite consuming, both in time as well as resources. So the idea of this webinar is we want to present some additional tools that can provide some pain relief for method development. And in particular, we're going to focus on a few software packages that ACDLabs offers to help people streamline their method development processes. So given a scenario, if you're working in an analytical chemistry lab, you're given a sample for separation and you're told, please separate, and I'm interested in one peak, or maybe there's a few peaks that you're interested in monitoring for. So ideally, you can put your sample on your HPLC and it's available for you, and you've got standard methods to run, and you get adequate separation, and then you're happy and you're able to report it back to the scientist that has put in this request. However, we understand that this is, we don't always live in an ideal world. So oftentimes there may not be a standard method available for your particular separation or your particular component of interest. So maybe there is a standard method available that you can tweak a little bit and you've got a starting point. So if I were to load a particular method and inject my sample, I can get a result and say, you know what, that result's okay, but I'm not happy with it. I think I can do better. I can tweak one particular property for optimization, and I could say, oh, you know what, that actually made it worse, so I want to change something else and change a different variable. And you say, okay, I can get this slightly better. And now you can see how you can get into an iterative trial and error process, and depending on how complex your separation is, this can be very time consuming, as well as it can eat up resources, say such as solvents, especially if the price of acetonitrile is going up. This may not be the most ideal path forward. So just to hit on a few things on chromatography optimizations, if you've got a particular separation, often your compounds of interest you want to have fully resolved. So in this particular example that I'm shown here on the screen, if I'm interested in peaks in this region, obviously this would require some particular optimization to get rid of this coelution. The fact that I have separation everywhere else on my chromatogram does not really matter for my particular scenario. Another particular scenario that could be presented is you're trying to develop a method for a release lab, so you need to cut down the time of your chromatographic separations. And often there are many variables that can be taken into account to lower the amount of time. So you can see how the problem can quickly snowball and become more complex. So the purpose of this webinar is we wanted to mention and highlight how software can help you with your particular method development. The first point that I would like to hit on is at ACDLabs we provide a vendor-neutral platform to perform any of your data analysis. So you can create methods on any of your HPLC, and then you can model and create models. It does not matter on whatever instrument the data was collected. You can make a model for separation for that particular instrument. In terms of modeling your data to get a good separation, you have the ability of using a linear model, and you can see how this would be simpler to do. However, we understand that reality, you may have to employ some nonlinear models as well. So you've got that flexibility within the software platform. There are some handy built-in tools to help with preparation of data, the main one being peak tracking. So if as you're doing method development and you're changing parameters, peaks can move relative to one another. So there are tools built into the software to automatically track the peaks between experiments. And finally, there are tools within the software to allow you to optimize particular parameters to meet the suitability criteria that you define for your separation, such as gradient, pH, temperature, and solvent concentrations. So to give you just a brief overview of our peak tracking tool, I've displayed here two method separations for the same sample. And in order for me to understand the impact of changing my particular variable, I need to know what's happening to each of my peaks. So I can quickly deduce that maybe this peak I'm able to track quite easily. But say this peak has moved relative to the second. So I can deduce and determine, say, that this may be the peak of interest. But you see, as peaks move around, this can actually become a very tedious and cumbersome project. And what this can do as an analyst is eat up a lot of your time and actually give you a lot of headaches and keep you out of the lab rather than being in the lab working on all the instruments. So in the processing piece of our software, there's a tool that we have called peak matching and peak tracking. And this works based on 3D data. And what the software actually does is, we see up top here, I've got my manual matching tool where each of the chromatograms are represented by the two lines, and each dot represents a peak. So when I click on a dot, it displays the UV visible spectrum down below, and it shows the matching criteria. For here, I've highlighted for component 8. So as the expert, I can then go through and review the matching results that the software has provided, and then determine whether or not the software has done an adequate job of matching the data. Now, in terms of method simulation and optimization, when you're performing and trying to optimize a particular method, it's very common to perform a few scouting runs where you're changing either maybe one or two variables to get the optimal separation. So what you can actually do is take your scouting runs and then feed it into another piece of software that will take your data provided and create a mathematical model of a chromatogram for the separation. And then using this mathematical model, you can set up suitability criteria and have the software again use a linear model or a nonlinear model to optimize things like gradient, pH, or temperature so that you can achieve the optimal separation. So now I would like to turn things over to my colleague Anne-Marie, who's actually going to go through the software and demonstrate to you how you can optimize different method parameters within the ACDLabs platform.
Thanks, Brent. So as Brent mentioned, one of the things that we actually do need for doing our optimization is to have peaks tracked within the software. Now, in this example, we can see that we have all of our peaks are labeled and that we have the corresponding retention times. If we move to a different sample, again, you can see the peak label and the retention time. Once this has been done, you can move forward with your optimization. So by selecting all of the experiments that you're interested in, you can then move to the Transfer to LC Simulator, and this is going to open up the software that will be doing the prediction for us. Now, when you get into the software, you have the opportunity to select the mode that you're interested in. In this case, we're going to be looking at gradient and temperature. Now, if you were interested in a different mode, you can simply select that. And if your mode does not exist, you can do another mode and create your own. So we're going to move forward here. And now we have this summary table that's created where we can see our peaks named and the corresponding retention time for each of the 4 experiments. You can also see that the gradient conditions and temperature have been pulled into the software from the metadata. If you'd like to see a little more detail on this, you can select one of the experiments and you can see now, specific for only that experiment, what parameters were used. You can do this for any of the 4 experiments. Before we move on to our modeling and optimization, we need to check a few parameters. Now, as I mentioned, a lot of your data is pulled in from the metadata with the software, but there are a few critical parameters that need to be filled out before proceeding with the optimization. And these are shown in bold. So what we're looking at is the dwell volume, our observed T0, and a flow rate. Once these fields have been populated, you can move forward. Now you can see the view of the software here, and it's asking whether we want to proceed with method generation. But at this time, I'm going to say no, so that we have a chance to look at the modeled chromatogram before moving on to optimization. Now, as Brent mentioned, the software creates a mathematical model for your experiments, and that is shown here in black. If you look slightly below this, you can see a line in green, which is indicating the selected experimental condition. Since those 2 values are overlaying quite well, it shows how well the modeled chromatogram is actually done. Now, in this, you can also see that there's 2 peaks here labeled in red. These peaks are known as the critical pair, which is also shown on the side here. This pair is where, when you set your minimum resolution, this is what is considered. So the critical pair being the 2 peaks alluding most closely to one another. From here we can see that we have a table of methods, which contains all of the experimental methods that we imported into the software, and will also contain any predicted methods that we move forward with. If we move towards our gradient editor and resolution map, we now have the opportunity to manually manipulate the chromatogram. So by selecting our point and dragging slightly, you can see that the gradient map, or the resolution map, as well as the chromatogram are automatically updated. In addition, you can see that there is an additional line added to the table of methods to populate this result. Now, we had just moved one of the peaks on our gradient editor. We could also do the same thing on our resolution map. So by clicking, you can see that the software is updated automatically. Now, rather than sit here and do a lot of manual manipulation, let's see what the software can actually do for us. So we're now going to look at setting our system suitability criteria. So in this case, we can see that we have run times that are typically around 50 and 80 minutes. So if we wanted to shorten this runtime, we might be looking at something maybe under 45 minutes, ideally less than 30. And so we can set this in our runtime here. We can also set the resolution, and this is going to be the minimum resolution required for the critical pair. And you can set your retention factor for your column. If we move over to the column stability criteria, we can set what temperature range we're interested in. Now, in order to get the most accurate prediction, I suggest staying close to the temperature values that you used in your experiments. So in the experiments that we ran, we were looking at 35 and 45 degrees. So I'm just going to extend those ranges a little bit to 32 and 47. Now that our system suitability criteria has been set, we can move forward with the optimization. The software prompts you automatically to say, are you ready to start generating methods? And this time, we're ready. all of our system suitability criteria has been pulled into the software, and now we're ready to go. So in about 2 seconds, the software has come up with 5 methods that have a suitability of 1. So that means meeting our resolution, runtime, and our temperature conditions. When we click OK, you can see that these 5 methods have been added to our table of methods. You can click on any of the methods and see the change in the chromatogram, the gradient editor, and the resolution map. Now you can see the parameters on the left-hand side of the screen have also been updated to include the system suitability criteria for the selected experiment. You still have the opportunity to manually tweak these values if you're interested in it. And if you're ready to tweak a chromatogram, if you lock your method, then you can move your peak without changing one of the predicted methods. It will create a new line in your table, so you're not losing any of your information. Now, another key component to developing methods is to ensure that your method is robust. So when I'm talking about a robust method, I'm referring to one where a slight change in the pH or temperature is not going to cause a great change to our method. So if we look at our resolution map, we can see these orange-red areas are the areas where we had a good meeting of our system suitability. And if we look at the blue regions, those are areas where that criteria was not met so well. So an ideal situation would be to be somewhere where you have a good region of the same color. So this would be, if you're standing in one spot, you want to be able to walk around a little and not have to worry about taking one step and falling off a cliff. Once we're happy with our optimization, you can then report this data out through our reporting feature. Alternatively, you can also import this into our processing tool and be able to use this for other experiments and comparisons and further manipulate the data. So with this, Brent, I think I'll pass it back to you.
Thanks, Anne-Marie. So the goal of this was to introduce the ideas to everybody on the different ways software can help, and we had shown how you can go through and create a model of your method that you're hoping to develop, as well as how you can tweak your separation parameters using our simulation tools.